shall start off with this topic. Okay, small topic we discuss kरूंगा, then I'll move towards the main important point. So today I'm going to discuss about the close packing of spheres. So next topic right now. Close packing of spheres. Okay, close packing of spheres. So number one, I'll be discussing about the close packing of spheres in one dimension. In one dimension. Okay, one dimension means along one axis. Two dimension means along two axes. Three dimension means along three axes. Arrangement along three axes. Okay. So see, there is only one way of arranging the particles along one dimension. One dimension may you will find that you'll see that there is only one way of arranging the particles. You can arrange the particles in a straight line like this. So there is no other way. There is no other way in which you can arrange this particles. So there is only one way, and we see that each sphere is in contact with how many other spheres, guys? Each sphere is in contact with maximum how many other spheres?
4.
4. Each sphere is in contact with 4. What's a sphere?
2. 1.
2. This sphere is in contact with this and this. This sphere is in contact with this and this. Okay, so the coordination number is equal to 2. So what is the definition of coordination number? Coordination number is defined as the number of spheres with which a given sphere is in contact. Coordination number is the number of, again, spheres with which a given sphere is in contact. Okay, fine, understood? Okay, so ये तो मतलब कुछ बात ही नहीं इसमें. So let us discuss along two dimensions now. ये तो हुआ along one dimension. Okay, now let us discuss along two dimensions. Okay. Now we have a layer of spheres. I am talking about a sphere out here, not a circle. I am talking about a sphere. So I have a layer of spheres out here. Now you tell me, where can you place the second layer of sphere? So there are two ways. One way of placing the sphere is directly on top of this. I can place the second layer directly on top of this. Now, do you see the center of the spheres coincide with each other? The center of the spheres, do they lie in a straight line? The different layers of spheres, does the center lie in the straight line? Yes, the center lies along the straight line. The center lies along the straight line. So this is one way of placing the sphere, and we can say lots of vacant spaces out here. Fine. Now you tell me, कोई भी एक sphere select कर लो. So ये sphere select कर लो. ये. So this sphere is in contact with how many spheres? ये जो sphere है, it is in contact with how many spheres?
4.
Okay, so what is the coordination number? The coordination number is equal to 4. Now, each layer is exactly identical to the other layer. यहाँ पर जो arrangement था, यहाँ पर भी वही arrangement है, यहाँ पर भी वही arrangement है. So if I label this layer as A type, this will also be of A type. This will also be of A type. So this is also known as here A dot type. A dot type. Each layer is identical, right? Okay. Now this sphere is in contact with 4 other spheres. Now let me join the center of these 4 spheres. ये चारों का sphere में draw कर लेता हूँ like this. Center. Now let me join the center of the spheres. कौन सा शेप आ रहा है ये? कौन सा शेप आ रहा है? स्क्वायर.
Square.
So this is known as a square close packing. Square close packing. This is known as a square close packing. Okay. और इसका जो पैकिंग एफिशिएंसी होगा ना, इसका पैकिंग एफिशिएंसी बहुत कम होता है, 50 लगभग 52% ऐसा होगा. पैकिंग एफिशिएंसी इज वेरी 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 लेस. ठीक है. Now can you suggest me any other ways of placing the second layer of spheres? So I'm just going to draw first layer of sphere out here. I'm going to draw first layer of sphere out here. ठीक है. Now यहाँ तो मैंने रखा था on top of this side. Where can you place the second layer of sphere, guys? Is there any other way? Yes, the second layer of sphere can be kept in between this voids. यहाँ पर जो depression है ना, ये depression में तुम place कर सकते हो. यहाँ पर. So it doesn't actually look like a sphere when I'm drawing, okay, but it will look like this. Again, third layer तुम यहाँ पर draw कर सकते हो. Okay, you can draw the third layer like this. So fourth layer फिर यहाँ पर draw कर सकते हो ना. So यहाँ पर भी तुम्हारा voids है, यहाँ पर भी voids है. Whatever voids are these है, ये क्या void बोलते हैं हम लोग इसको? Triangular. Very good. Triangular void. Excellent. Triangular void. Now you select any one sphere. चलो ये sphere select कर दिए. So this sphere is in contact with how many other spheres?
6.
6. कौन सा 6? 1, 2, 3, 4, 5, 6. Now, if you join the centers of the 6 spheres, so join कर लेते.
Hexagonal.
क्या आना चाहिए?
Hexagonal.
Hexagonal. So this is known as a hexagonal close packing in 2 dimension. This is known as a hexagonal close packing 2 dimension. What is the coordination number, guys?
6.
6. Very good. Coordination number of 6. Now, the arrangement of first layer and third layer, are they exactly the same? हाँ, देखो ना, center भी coincide कर रहा है. But the arrangement of second layer are different. If you keep a fourth layer and second layer will look alike. Arrangement of fourth layer and second layer will look alike. Yes. Yes. So if I label this as A, so this has a different arrangement. I must label this as B. Third को में A. So this is also known as what? This is also known as here A B dot type है. और यहाँ पर देखने से पता चल रहा है voids, vacant spaces कहाँ ज्यादा है? ये A टाइप ना A B टाइप में. Voids कहाँ पर कम है? Packing efficiency कहाँ पर ज्यादा है? Hexagonal ना square close packing में. Hexagonal में they are more closely packed. इसका packing efficiency ज्यादा है. इसका packing efficiency लगभग तुम्हारा 62 ऐसे होगा. 64% ऐसे. ओके ठीक है. पैकिंग एफिशिएंसी इसका ज्यादा है. ओके जस्ट गिव मी अ मोमेंट.
What is this CN? CN coordination number.
Okay, so let me just check the exact this thing. Okay, I don't remember. 52.4 लिख लो इसका, कितना लिखा लो? 52 ना, square close packing का 52.4%. Okay, and 60.4, not 64, it's 60.4. चलो, 2 dimension में it's understood?
Yes, sir.
No problem? Any problem? Clear?
No, sir. Sir,
No.
how did we get those packing efficiency values?
You can easily calculate. वही होगा hexagon, ये total area of the hexagon में, what is the total area of this circles? कर सकते हो calculation. Okay, no need to do, but ये जैसे square है, square में total how many spheres are there inside the square? 1/4, 1/4, 1/4, 1/4, 1 plus 1 2 कर सकते हैं. मैंने तो करवाया है ये तो. Now the problem तो नहीं बोलूंगा मैं. Now the challenge comes when we discuss about the close packing in 3 dimension. If we discuss the close packing in 3 dimension, along 3 dimension, okay. अब देखो. So first of all, I'll start off with your square close packing. मैं यही से start करूंगा, square close packing. I'll start off with your square close packing in this. Okay. Fine. I've started off with a square close packing. Now, these are spheres, remember, these are balls. Now, how can you keep the second layer of sphere? Now, suppose ये जो ball है, sphere है. Can I keep the second layer of sphere on top of this? इसके ऊपर रख सकता हूँ मैं? इसका ऊपर रख सकता हूँ मैं? Can I keep like this?
Yes, sir.
Yes, sir.
Can I keep like this? So if I keep like this, the first layer and the second layer will have exactly the same arrangement.
Yes, sir.
Yes or no?
Yes, sir.
Obviously, if I keep on top of this, the first layer and the second layer will be exactly identical. Right? So since the first layer and the second layer will be exactly identical, okay. मतलब इसका ठीक पीछे रख रहा हूँ मैं. इसका ठीक पीछे है सर. I have a second layer out here. I have a second layer out here. यहाँ पर रख रहा हूँ. Okay, so this is known as a type thing. This is known as a type. Now, देखो इसको I can't draw in the board. Now I can't draw in the board. So just give me a second. I'll just show you in the video. Okay, just give me a moment. अब देखो.
Possible linear one-dimensional arrangement possible with spheres. They queue up linearly, each sphere touching the adjacent spheres like this. Packing in 2 dimensions. To arrange spheres in 2 dimensions, we take the linear one-dimension arrangement that was shown previously.
देखो.
There are 2 ways by which we may arrange the spheres in a 2-dimensional platform.
Sir,
They
please
may be
increase the
arranged
volume.
separately. Note that each linear
Huh?
Sir, the volume.
I'll increase it.
Yes, sir.
are aligned vertically. Here, the vacant space is this. Now, in this packing, the spheres take up only 52.48% of the available space. Here, a single sphere touches 4 other spheres. If we join the centers of the spheres, we get a square. Therefore, this packing is called square close packing. A second way of arranging the linear one-dimensional arrangements is to keep the spheres of the second linear one-dimensional arrangement in the depressions of the first, like this. Here, every alternate linear arrangement has the same alignment. These are the vacant spaces, which is visibly less than the square close packing and hence more efficiently packed. In this packing, the spheres occupy 60.4% of the available space. The voids created in this packing touches three spheres forming an equilateral triangle and are called triangular voids. A single sphere touches six other spheres, and by joining the centers of these spheres, we get a hexagon. Therefore, this packing is called hexagonal closed pack. Packing in 3 dimensions.
अब देखो
Making square closed pack 2-dimensional layers. This is done by placing a 2-dimensional layer just above the first layer and so on. All the layers.
now does every layer look identical to the other layer?
Yes, sir.
Yes.
So मतलब क्या टाइप का होगा ये ए टाइप का. Now if I join the 4 closest sphere, कौन सा मतलब unit cell कैसा आएगा बोलो तो. If I join the 4 atoms, तुम visualize करो तो you are joining the 4 atoms which are in contact with each other. तुम्हारा unit cell उसका center join करेगा तो कैसा आएगा? Cube आएगा. Yes, exactly.
Yes, sir.
Exactly. इसका center, इसका center, इसका center, इसका center join किया मैंने. और इसके पीछे जो है इसका भी सेंटर ज्वाइन किया, इससे इसका सेंटर ज्वाइन किया, तो मेरा जो रिपीटेशन होगा यूनिट सेल वो क्या आएगा तुम्हारा स्क्वायर क्यूब आएगा. क्यूब ओके, सिंपल क्यूब आएगा. ठीक है, देखो यूनिट सेल दिखाएगा.
Taking hexagonal closed packing 2-dimensional way.
Okay, now this is important. Now this is important. Okay, so the first layer we have started earlier. We have started with the square closed packing. Now here we have started off with what is this packing known as? 2 dimension में a given sphere is in contact with 6 other spheres. So this is hexagonal closed packing. This is a hexagonal closed packing. Okay. Now what type of voids do you see out here? What type of voids do we see? Triangular voids. So we see a triangular voids out here. So what we do is we keep the second layer of sphere on top of this triangular voids. यहाँ पर रखेंगे हम लोग. यहाँ पर रखेंगे. We keep the second layer of spheres on top of this like this. ठीक है? अब देखो.
The first layer contains red colored spheres indicating the alignment of the layer. This alignment is called A.
So ये arrangement is known as A.
These are the void spaces of the layer.
Triangular voids.
We have to place a layer on top of this layer. For efficient packing, we will have to place the second layer in such a way that the spheres are exactly over the triangular voids of the first layer.
I will keep the
Only
second
these
layer.
triangular voids can be covered.
Okay. Now यहाँ पर क्या बोल रहा है? देखो. I'll just rewind a little bit.
A. These are the void spaces of the layer.
You are
We have to
keeping.
place a layer
Yeah.
on top of this layer. For efficient packing, we will have to place
यहाँ
the
पर
second
रखना है
layer
यहाँ पर.
in such a way that the spheres are exactly over the triangular voids of the first layer. Only these triangular voids can be covered.
Okay. Just a minute.
We will have to place the second layer in such a way that the spheres are exactly over the triangular voids of the first layer. Only these triangular voids.
Okay. So यहाँ पर क्या हो रहा है? Now I'm just phrasing this screen. So I'm placing the spheres on top of this. समझे बात को? I'm placing the spheres on top of this. I'm placing sphere on top of this. यहाँ पर. So are all the triangular voids filled up? Are all the triangular voids occupied?
No, sir.
यहाँ पर रख रहा हूँ मैं. ठीक है, यहाँ पर रख रहा हूँ, यहाँ पर रख रहा हूँ, यहाँ पर रख रहा हूँ, यहाँ पर भी रख रहा हूँ, यहाँ पर भी रख रहा हूँ. But these
No, sir.
triangular voids are not occupied. Eight triangular voids are not still occupied. Even after placing the second layer, these triangular voids which are marked by this white, these are not occupied. यहाँ पर सिर्फ place करोगे. So how does it look like? Let us see.
Can be covered. The spheres of the second layer are blue in color, which indicate that this layer has different alignment.
They have a different
This
alignment.
is called P. We can no longer see.
Okay, now देख. Now ये जो तीन स्फीयर था और ये जो एक स्फीयर इसका ऊपर आया, so ये इसके बीच में तो एक void create होगा. What is the void between these 4 spheres known as? ये 4 स्फीयर के बीच में एक void create हो रहा है यहाँ पर. What is that void? Tetrahedral. Good, excellent, very good. And ये जो 3 स्फीयर है यहाँ पर जो 3 स्फीयर है, and ये जो 3 स्फीयर है यहाँ पर भी एक void create हो रहा है. What is this void known as? Octahedral. Excellent. So after you place the second layer of sphere, there are two types of voids created. एक यहाँ पर तुम्हारा tetrahedral void create होगा और यहाँ पर तुम्हारा octahedral void create होगा. Okay. Now यहाँ पर जो second layer of sphere का जो void है ना यहाँ पर triangular void, are these involved in making octahedral void? ये void are these involved in octahedral void? ये तीनों का बीच में this void is involved in making octahedral void, not this, right? समझ में आ रहा है? So these are ये तीन sphere के बीच में this void is involved in the octahedral void, not this, right? ये तीनों के बीच में this is not involved in the octahedral void. Now इसको मैं transparent कर दूंगा. देखो.
All the void spaces created between the two layers.
देखो.
In order to overcome this problem, we have to make the second layer transparent.
अब दिखा दे रहा क्लियर ट्रांसपेरेंट बना के ये क्या कौन सा वर्ड है?
Yes, sir.
ये कौन सा वर्ड है? Tetrahedral. ये कौन सा वर्ड है? Octahedral. And second layer of sphere का this triangular void, ये जो triangular void है second layer का बात कर रहा हूँ मैं. Second layer का जो ये triangular void है, these are not involved in the octahedral void है. ठीक है? और ये इसका triangular void it's involved in octahedral void but not this void है. ठीक है? समझ में आ रहा है मैं क्या बोल रहा हूँ? Okay.
We can clearly see the two different types of voids created by these two layers. These are called tetrahedral voids, marked by the letter T. And these are called octahedral voids, marked by the letter O.
अब देखो. Now I'll place the third layer in between the triangular void of the second layer which are not involved in the octahedral void. मतलब मैं जो third layer रखूंगा कहाँ पर रखूंगा? Will I keep out here? No. Will I keep out here? No. मैं कहाँ पर रखूंगा? I'll keep the third layer on the triangular void of the second layer. I'll keep the third layer on the triangular void of the second layer. यहाँ पर रखूंगा. पर यहाँ पर रखूंगा तो ये जो फर्स्ट लेयर और ये जो थर्ड लेयर दे आर डायरेक्टली मतलब ऑपोजिट टू ईच अदर. देखो तो यहाँ पर एक स्फीयर है, इसका ऊपर रख रहा हूँ मैं और एक स्फीयर. सो ये लेयर और ये लेयर का सेंटर ज्वाइन हो रहा है.
Yes, sir.
यहाँ पर रख रहा हूँ मतलब ये स्फीयर और ये स्फीयर का सेंटर ज्वाइन हो रहा है. सेंटर ज्वाइन हो रहा है मतलब दे आर एग्जैक्टली द सेम. देखो. सो दिस वन वे ऑफ प्लेसिंग है.
The tetrahedral voids are created by four spheres.
देखो tetrahedral void दिखा रहा है. इसको
First,
सेपरेट
we
करो.
make the spheres a little smaller in order to
Join the
understand.
centers.
Then we join the center of the spheres.
It looks
by
like a
spheres.
tetrahedral.
The shape is regular tetrahedral.
भाई वही चीज समझा रहा तुम लोगों को tetrahedral void.
So the void is called tetrahedral void. The octahedral voids are created by six spheres. Here also we make the spheres a little smaller, then join the center of the spheres to get the shape. The shape is a regular octahedron. Placing the third layer.
अब ये देखो.
This can be done in two ways. These are the triangular voids of the second layer that are not involved in making octahedral voids with the first layer.
Got it?
By placing the third layer
Yeah,
of these
but-
voids is one way of placing the third layer.
So the first layer, third layer looks
If we do
exactly
this,
the same.
we can see that the first and the third layer have the same alignment A. With similar reasoning, we keep a fourth layer on top of the third layer and see that the second and fourth layer have the same alignment B.
AB type. AB
This
type.
pattern of close packing is called AB type pattern.
In 3 dimensions. Now
We
इसको
make
छोटा कर
spheres
दो.
a little
छोटा.
smaller and join the centers with straight lines to understand the shape.
So I'm making the sphere smaller and joining by straight line.
It is my belief that this is the unit cell of this close packing because it is the smallest unit
There is the
that
repeating
may be
unit.
repeated to form the entire crystal. The top of this unit cell has the shape of a rhombus having gamma equal to 120.
ये नहीं चाहिए.
Three such rhombus form a hexagon. For better visual cognizance, this shape is taken as the unit cell of this close packing.
Okay. So the basic, okay, इसको थोड़ा सा और rotate करें.
hexagonal goes back or simply A.
So this is the smallest repeating unit. ये जो arrangement हम लोग ने देखा अभी, so this is the smallest repeating unit, right? So it's a hexagonal close packing or HCP structure. हम लोग ने किया था voids में. I told you HCP structure. HCP structure का repeating unit और unit से looks like this, right? ठीक है? So ये first layer, second layer, third layer. Now see, अब इसके ऊपर भी I think ऐसा ही होगा. इसके ऊपर, इसका ऊपर जो होगा ऐसा ही होगा. Yes. Now see, this sphere is in contact with how many spheres? 1, 2, 3, 4, 5, 6, 7, 8, 9. ऊपर 3, 9, 10, 11, 12. So this sphere is in contact with 12 other spheres, right? ये यहाँ पर 3, यहाँ पर 3, नीचे 3, ऊपर 3. So what is the coordination number of HCP? What is the coordination number of HCP?
12.
12. Coordination number of HCP is 12. The coordination number of HCP is 12. Okay, so this is the basic repeating unit. So HCP close packing structure means this. Close packing structure means this. Okay. उत्तर क्वेश्चन है यहाँ पर. HCP means AB type, right? AB type मतलब HCP. Okay. So the इसमें AB type में what is the basic repeating unit? Unit से क्या होगा? Hexagonal close packing. Okay.
P structure.
The other way of arranging.
Another way of placing the third layer is to cover the octahedral.
इसके आगे क्या किया था हम लोग ने? Where did we keep the third layer? Third layer यहाँ पर रखा था. Now in this method, in this way, in this alignment, what will I do? I'll keep the third layer on top of this. Right? कहाँ पर रख रहा हूँ मैं? कहाँ पर रख रहा हूँ third layer? Where am I keeping the third layer? In the on top of the. कहाँ पर रख रहा हूँ? यहाँ रख रहा हूँ मतलब ये क्या void है?
Octahedral void.
I'm keeping the third layer on the octahedral void. Now, is the third layer identical to any of the layers?
No,
Is
sir.
the third layer identical to any of the layers? Yes or no?
So first,
No.
ना first कैसा होगा? इसका center और यहाँ तो कुछ है ही नहीं. So third layer is also different. देखो इसका arrangement different हो रहा है. Third layer. देखो. I'm keeping on top of the octahedral void now.
Layer by placing the spheres of the third layer above the octahedral voids
वहाँ पर
made
रख
by
रहा
the
हूँ.
first two layers. The alignment of the third layer is different from
Different.
the first two layers, and so the color of the spheres have a different color, that is green color. Let this alignment be called C.
C.
Using the same reason, we can cover the octahedral voids made by
Now-
the second and third layers by a fourth layer.
Fourth layer में if I keep the fourth layer, देखो ये fourth layer का.
Let this alignment be called C.
अब देखो. If I keep the fourth layer on यहाँ पर मैं इसका और इसका octahedral void में मैं fourth layer रखूंगा तो ये fourth layer का center और कौन सा layer का center coincide कर रहा है? देखो ये यहाँ पर ऊपर रख रहा हूँ.
A
The
or
center of which layer and which layer will coincide?
A.
The center of fourth layer and the first layer they are going to coincide. So A, B, C फिर से कौन सा repeat हो रहा है?
A.
ABC type. इसको हम लोग ABC type बोलते हैं. ठीक है? Fine. So if I keep this sphere on top of this, it seems that the center of the fourth sphere and that of the first sphere इसका center coincide हो रहा है. So मतलब first layer और फिर से repeat हो रहा है. देखो.
sir,
Using the same
Sir.
Yes.
sir, the A र C चाहिँ कसरी भयो sir? त्यो बुझिन त.
देखो, this is a different arrangement. ये एक arrangement है. ये arrangement को red arrangement को we call it A. The second arrangement is different from the first arrangement, so we mark this second arrangement as B. And the third arrangement is also different from the other two, so we mark this arrangement by a different letter C. But as I keep the fourth layer, it is seen that the fourth layer and the first layer arrangement are same. So ये कौन सा arrangement हुआ? कौन सा type का? Second, first, second और third का similar है. First के साथ similar है, so इसको फिर से A बोलते हैं. मतलब ABC मतलब arrangement को हम लोग mark कर रहे हैं. First arrangement is marked as A. ये first layer को हम लोग A mark कर रहे हैं. Second layer is different from the first. We mark it by a different alphabet B. The third arrangement is different again. It's different arrangement. We mark it as C. ठीक है, fine. So just alphabets used to denote the arrangement. है कुछ ये नहीं है.
We can cover the octahedral voids
Octahedral cover
by the
कर रहा है.
second and third layers by a fourth layer.
So देखो
It will be found that the fourth layer has the same alignment as the first layer.
same देखो center coincide कर रहा है.
So this pattern is called ABCA.
इसका center देखो coincide कर रहा है. इसका
Now
center
again, making the spheres little smaller and joining their centers by straight lines, we get the shape of this pattern like this.
इसका
The
unit
unit
cell
cell of such a pattern is this.
इसको turn करो.
Face-centered cubic patterns.
इसको what is this? Face center.
Packing.
ये क्या बन रहा है? Face center देखो नहीं. Face center ही 8 corners में 8 corners में 8 है like this. And center का face में एक है. ठीक है. So what is the unit cell of ABC type? face centered. And ये पैकिंग को हम लोग cubic close packing बोलते हैं.
Called cubic close pack.
Cubic close pack.
Or
Same thing. CCP और FCC structure. ठीक है? Fine. Understood? पक्का?
Hi.
Okay. So any questions? So you have a fair idea now, right? We got a fair idea about the close packing. Yeah, chalo. Okay. So we discussed the voids also. We discussed coordination number.
Sir, please zoom out.
Yes.
Zoom out.
Board on Choma Bosha.
Well, done.
Yes, sir.
Okay. Now we will be discussing some very important topics. So pay attention. Okay. Okay, now we have done the first part is over. Right? First part is over. First question is over. Okay. So now we will be discussing today. So I'll just start off quickly with the second important topic. Okay. Chalo. So listen, ideal and non-ideal crystalline. Ideal and non-ideal crystal. Okay. Or ideal crystal is also known as a perfect crystalline. And non-ideal is also known as an imperfect crystal. Ideal and non-ideal crystal. Okay, so a crystal in which the constituent particles a crystal in which the constituent particles have a definite repeating arrangement. Have a definite repeating arrangement is called an ideal crystalline. Okay, now what does this mean? So ideal crystal में क्या होगा? There is a definite pattern of arrangement of particles. है मतलब क्या है? Let me try to explain it. Diagram देखो जितना भी क्वेश्चन आने वाला तुम लोगों को बोर्ड्स में सब diagrammatic question will come है. So you should understand the diagram है. A diagram we should understand. ठीक है? डायग्राम समझना बहुत इंपॉर्टेंट है. सो आइडियल क्रिस्टल में क्या होगा? आइडियल क्रिस्टल और परफेक्ट क्रिस्टल मतलब सपोज देयर आर टू पार्टिकल्स से ए बी. सो there is a definite regular arrangement of particles like this. There is a definite regular arrangement of particles. So these particles can be atoms like this, or it can be ions as well. It can be ions as well like this. So यहाँ पर कोई irregularity दिख रहा है? Do you see any irregularity out here? No. So it is an example of a perfect or an ideal crystal. So this figure, it represents an ideal crystal. But ideal crystal is only hypothetical, right? But as the temperature increases, what will happen to these particles? It will begin to vibrate. They cannot move here and there, obviously solidly, but they can vibrate. Eh? So due to vibration, one or more of these particles may leave the position. So ideal crystal is possible only at absolute Kelvin, only at 0 Kelvin. 0 Kelvin में क्या होगा? The molecular motion ceases. Right? There will be no molecular motion. Vibrate भी नहीं करेगा इतना absolute 0 में. So only at absolute 0, the particles will be in their respective position. Only at absolute 0, the particles will be in the respective positions. Again, at other temperatures, there might be some particles may be missing. Okay. So that gives rise to defect in a crystalline. Okay. So imperfections or defects in a crystal is the departure of the constant particles. Okay, here लिख लो. ये लिख लो second. Defect in a crystal और imperfections भी बोलते हैं इसको. I'm telling you, imperfections भी बोलते हैं, defect भी बोलते हैं. So defect in a crystal, okay, is the departure of the constituent particles. Is the departure of constituent particles. Is the departure of constituent particles of the crystal from its regular positioning. From its regular position in the lattice. So defects in a crystal, मतलब perfect crystal में सब अपना अपना position में रहेगा. Perfect, there is absolute order है. But say defect कब arise होगा? It is the departure of the constituent particles from its regular position. When the particles are no longer present in the position where it should be. If the particles are no longer present at the positions at which it should be present, then we say a crystal में क्या हो रहा है? Imperfections आ रहा है और defects आ रहा है. समझ में आ रहा है? So if the particles are missing from the regular position, then the crystal is said to possess some defect or तुम्हारा imperfection. ठीक है? Now again, ये जो defects in a crystal है, defects are of two types. So till you explain, guys. Okay, so
Yes, sir.
defects are of two types. So Chal, give me a minute. I'll just drink water and come back. It should be वो defective हो जाएगा और imperfect हो जाएगा. ठीक है? And defects are of how many types? Guys, defects are of two types. एक ये तुम्हारा line defect, which is not on syllabus. ये नहीं पढ़ना पड़ेगा. The other is a point defect. Right? Okay, one is a line defect, the other one is a point defect.
Sir, both are not there in the syllabus.
One is there. Oh.
Okay.
One is there. So these are very easy things, sir. You don't have to study. आज का आज ही पता चल जाएगा, आज का आज ही समझ में आ जाएगा. You don't need to study as well. मतलब रट्टा नहीं मारना पड़ेगा मेरा. Obviously, you need to study. So point defect is that. So when does a point defect arise? So point defect are the defects which arise due to deviation. They arise due to deviations of atoms or ions from the lattice point से मतलब अगर एक point से suppose this is a lattice point. Lattice point मतलब the points which are occupied by atoms or ions, right? The imperfections due to the lattice point. Lattice point means something is missing, something is not there, or some party other than B, some other particles are present. Okay, so the defect which arises due to lattice points. So the defects which arises due to lattice points are known as a point defect. Okay, these are known as a point defect. Okay.
Yes, sir.
Okay, now listen very carefully. Listen very carefully. A board is visible. मुझे तो black दिखाई दे रहा है.
दया है.
Okay.
It's also right.
Okay, fine. So let us discuss the defects now. Okay, point defects again. Let us discuss point defects. So if you can copy it simultaneously. Okay, along with me. So the two types of point defects. So the two types of point defects. Sorry. The two type of point defects. So number one is stoichiometric. Okay, stoichiometric defect लिख लो. And the other one is here non-stoichiometric defect. Okay. So first I'll explain you diagrammatically. Right, I'll explain you diagrammatically. Now you can ask me lots of questions out here. If you have any questions, please do ask me. So on the point defect, the point defects, as I told you, they can be classified into two types. One is a stoichiometric, the other one would be a non-stoichiometric point defect. So just diagrammatic, I'll draw one diagram. Okay. So the lattice points can either be represented by this circle or by this square. So exam में कुछ भी दे सकता है तुम लोगों को. So this represents the lattice points. This represents the lattice point. So lattice point means these positions are occupied by some particles, and the particles might be atoms or they may be ions. Okay, fine. So suppose these lattice points occupied by ions. So what are the ions? Say A positive and B negative. So I mark this cations by blue. I mark this cations by blue. Okay. And I have marked these anions by red color like this. So there are two types of particles out here, the positive ions and the negative ions. So what type of crystal is this? What type of crystal have I drawn? What type of crystal have I drawn? Yes, guys?
Ideal.
I have drawn an ideal crystal. ये तो ideal crystal है ना? It's ideal crystal. And tell me what is the ratio of cations and anions out here? What is the ratio?
One.
So you know, for every 6 cations there are 6 anions. The ratio 6:6 होगा, or the ratio is
1:1.
1:1. The ratio is 1:1. Okay, fine. Okay, till here it's perfect. No issues. Sure. ठीक है. Now let me just draw. You don't draw. मतलब ये draw करो. मतलब पूरा complete मत करो ये. First have a look, then I'll give you time to copy. First have a look, and then I'll give you time to copy.
Go ahead, sir.
Oh.
That is okay. Again, your ideal crystal over. Now listen very carefully. Just concentrate on the board. Now what will I do? Now suppose from one of the lattice points A is missing, and from the other lattice point say B is missing. Eh? Now, is this an ideal crystal or a non-ideal crystal?
Sir, non-ideal.
Non-ideal. And इसको point defect हो रहा है क्योंकि some lattice मतलब particles are missing from the lattice points. So यहाँ पर क्या है defect arise हो रहा है. So यहाँ पर एक defect arise हो रहा है. So यहाँ पर क्या arise हो रहा है तुम्हारा defect arise हो रहा है. Now यहाँ पर ये जो non-ideal crystal है यहाँ पर जो defect हो रहा है, okay, defect हो रहा है पता चल रहा है. But here again, what is the ratio of positive and negative ions? क्या है ratio?
1:1.
1:1. So यहाँ पर क्या चीज दिखा है? In spite of the defect, the ratio of positive and negative ions are same as that in an ideal crystal. So यहाँ पर तो defect हो रहा है. There is a defect. We can clearly see there is a defect. Arrangement of regular नहीं है. There is a defect, but in spite of the defect, the ratio of positive and negative ions are same as that in an ideal crystal. So this type of defect is known as your stoichiometric defect. So how are you going to define a stoichiometric defect? Yes, Aditya, how are you going to define a stoichiometric defect? कैसे define करोगे? So those defects, in spite of the defect, if the ratio of particles are same as that of an ideal crystal, in spite of the defect, if the ratio of particles are same as that of an ideal crystal, then the defect is referred to as stoichiometric defect. So हम लोग यहाँ पर छोटा सा definition यहाँ पर करेंगे. So stoichiometric defect में क्या होगा? In spite of the defect, the ratio of particles will be same. In spite of the defect, the ratio of particles will be same as that in an ideal crystal. In spite of the defect, the ratio of particles will be same as that of an ideal crystal. So this defect is referred to as a stoichiometric defect. So diagrammatically questions might come. तुम लोगों को ये diagram दे देगा. So this represents which type of defect? चारटा option. Stoichiometric, non-stoichiometric, दो कोई defect दिए. So ये stoichiometric हुआ क्योंकि ratio maintain हो रहा है. ठीक? Is it understood?
Yes, sir.
पक्का?
Yes, sir.
Okay, this is too easy for you all. Right? ना? So stoichiometric मतलब defect हो रहा है लेकिन defect के मतलब in spite of the defect, the ratio of particles will be same as that in an ideal crystal. ये आया तुम्हारा stoichiometric. ठीक है? Now यहाँ पर, so are you going to copy this? Will you copy this?
Yes, sir.
I'll go on explaining this. I'll explain now another thing.
Yes, sir.
So मान लो
So
यहाँ पर A positive है, यहाँ पर A positive है. Now is the ratio of, what is the ratio of the ions now? What is the ratio now?
5 is 6:5.
6:5.
So is this equal to that of an ideal crystal?
No, sir.
Is this the same as that in an ideal crystal? No, the ratio is not same. Eh? The ratio is not same. So if because of the defect, the ratio of particles is not same as that in an ideal crystal, then the defect is referred to as non-stoichiometric defect. A defect होने के बाद भी ratio same है ideal crystal का, that is a stoichiometric defect. But because of the defect, if the ratio is not same as that of an ideal crystal, this comes under here non-stoichiometric defect. This comes under here non-stoichiometric defect. Okay. So I'm not writing the definition of non-stoichiometric. I hope you all can do write it on your own. ना लिख सकते हो?
Yes, sir.
Chalo, good, very good. So I think this part is understood now. Okay. So all okay till here? All okay till here? Can I move to
Yes,
the next
sir.
topic?
Yes,
Okay,
sir.
fine. So I'm moving to the next topic. Okay, so I have explained in details stoichiometric defect क्या है, non-stoichiometric defect क्या है. Okay, now stoichiometric defects are of two types again. You just it's just like a story. ये मतलब एक story का जैसा है. Okay, there's nothing rocket science out है, मतलब एक ही बार में समझ में आएगा. Stoichiometric मतलब same defect के बावजूद तुम्हारा the ratio of particles will be same as that of an ideal crystal. So stoichiometric defects are of two types. What are the two types? So number one is your Schottky defect. Schottky defect. Okay, number A is your Schottky defect, and the other one is a FRENKEL defect. Schottky and FRENKEL. Okay, so first I'm going to discuss about your Schottky defect. Okay, now I'm going to discuss about your Schottky defect. Okay, you just concentrate on the board. I'm not going to draw again. I'm going to use
Sir,
yes.
so those are like the types of stoichiometric defect.
Yes, there are two types of stoichiometric defect. There are two types of stoichiometric defect.
Yes, sir.
एक है तुम्हारा Schottky defect, एक है तुम्हारा Schottky defect. One is a Schottky defect, and the other type of Schottky defect is known as a FRENKEL defect, which I am going to discuss afterwards. FRENKEL. एक है Schottky, दूसरा है तुम्हारा FRENKEL defect. ठीक है? So first I am going to discuss this in detail. I am going to discuss Schottky defect. Now you draw the diagram. Diagram मतलब very important है. ये कौन सा क्रिस्टल बना रहा हूँ मैं? कुछ डिफेक्ट है इसमें?
No, sir.
कुछ डिफेक्ट है? No, it's not defect. ये तो perfect crystal है. Perfect crystal है. Now एक cation missing है, एक anion missing है. Now ये stoichiometric है ना non-stoichiometric है? रेशियो मेंटेन हो रहा है, एक कैटायन कम हो रहा है, एक एनायन कम हो रहा है, लेकिन रेशियो तो मेंटेन हो रहा है. सो स्कॉटकी डिफेक्ट में क्या हो रहा है? ये equal number of cations and anions are missing from the lattice side. Say. So for every one cation missing, if one anion is missing, equal number, or if same number of cation and anion are missing, then this defect is referred to as your Schottky defect. So diagram आएगा तुम लोग, I'm telling you, Schottky defect बोलते हैं इसको. So this defect will be referred to as a Schottky defect. So Schottky defect में how are you going to remember? S for Schottky, S for same. Same number of cations and anions are missing from the lattice sites. Schottky defect में same number of cations and anions will be missing from the lattice sites. Same number or equal number of cations and anions are missing from the lattice sites. Got it? समझ में आ रहा है? Okay, so ये तो stoichiometric है, पता चल रहा है diagram से. So stoichiometric में what type of defect again? Schottky. How are you going to remember? S for Schottky, S for same number of cations and anions will be missing from the lattice cells. Now important चीज यहाँ पर, what are the consequences? What are the consequences of the Schottky defect? What are the consequences of Schottky defect? Okay, number one. So due to, as a result of Schottky defect, now you tell me density of crystal क्या होगा? What will happen density? Now the ions are missing, eh? Ions छोड़ के चला जा रहा है lattice sites. The ions are no longer to be seen. So what do you think will happen to the density of crystal? It will remain the same, increase over decrease over. Yes?
Decrease.
Very good. The density of the crystal decreases. The density of the crystal decreases. So as a result of Schottky defect, the density decreases. Okay. Why does the density decrease, guys? Why does the density decrease?
Because the mass per volume decreases.
Because the ions are leaving the lattice site. Say, the number of ions decreases. The number of ions decreases, the density of the crystal will also decrease. Okay, fine. Now, second, so the crystal remains. Now, due to defect, what is the number of positive charged ions? How many positive charges are there? How many positive charges are there? 5? 1, 2, 3, 4, 5. How many negative charges are there? 5? 5. 1, 2, 3, 4, 5. So, ये तो stoichiometric defect है ना, जितना cation होगा उतना anion होगा. मतलब the number of positively charged cations is equal to the number of negatively charged cations. So due to balancing of charges, remember the crystal remains electrically neutral. The crystal remains electrically neutral. Okay, you can just mute yourselves. Background noise aa raha hai. You can just mute yourselves kindly. Okay, so the crystal remains electrically neutral. Since the charges are balanced, it will be electrically neutral.
Yes, sir.
Fine. The third one is, यहाँ पर एक hole create हो रहा है, यहाँ पर एक void create हो रहा है, empty space create हो रहा है. So due to this empty space, what will happen? The stability of the crystal, the stability of the decreases. The stability of the crystal decreases. And now, यहाँ पर holes create हो रहा है. So the ions, मतलब पहले क्या था? The movement of ions was restricted ideal में. But now the ions can move from one place to another, right? So the movement of ions मतलब electrical conductivity increase हो रहा है. Okay. So the electrical conductivity increases. Yeah, electrical conductivity increase. So these are the consequences of your Schottky defect. Eh? These are the consequences of your Schottky defect. Okay, I think it's understood. Yes.
So if ions are decreasing, then conductivity पनि decrease हुनु पर्दैन.
No, conductivity is due to what? Conductivity is due to movement of ions. So यहाँ पर तो these ions can move here, these ions can move here. So now the movement of ions becomes possible. Right?
Yes, sir.
That is why the electrical conductivity increases. Okay. Fine. So these are the consequences of Schottky defect. These are the consequences of Schottky defect. Now let us see the conditions. Let us see the conditions. Let us see the conditions for Schottky defect. Okay. So condition is number one, the cation and anion must be not same, I'm not writing same, must be similar in size. Matlab, the size of the cations and anions must be similar. For example, alkali metal halides. For example, alkali metal halides. That's NaCl, NaBr, your cesium chloride, your cesium iodide, and AgBr. AgBr को underline कर लेना. So यहाँ पर the size of sodium ion and chloride ions are similar, not same, obviously. Okay, so it is condition here. Tomorrow the size of the cation and anion must be similar. So these type of crystals, they show Schottky defect. Number one. And number two, we have not studied yet. You will understand it afterwards. They are exhibited by crystals. They are exhibited by crystals having high
Sir, what is
coordination
CS?
number. Okay, so ये मैं बाद में समझा दूंगा. Why NaCl has a high coordination number, वो बाद में समझ में आएगा. Okay, so just लिख लो. They are exhibited by crystals having high coordination number.
Yes, sir.
Okay, so from the diagram, it's एक रट्टा नहीं मारना पड़ेगा. Ions missing, density decreases. Holes create हो रहा है, packing efficiency कम हो रहा है, so stability decreases. The ions can move here and there now, so electrical conductivity increases. But the crystal as a whole remains electrically neutral क्योंकि ratio of cations and anions are still the same. बस ये तो चार तो देखना ही नहीं पड़ेगा. Conditions, sizes of cation and anions must be same. इसीलिए alkali metal halides, and the crystals again should have high coordination number. Okay, so these are your conditions for Schottky defect.
Yes, sir.
Fine. Anything to ask out here?
Yes, sir.
Okay, chalo. So if you have nothing to ask, then I'll finish off this topic today. So next मैं तुम लोगों को दिखाऊंगा Frenkel defect. So there is every chance ये दोनों defect में confuse हो जाओगे एग्जाम में. इसलिए मैं बोल रहा हूँ Schottky defect कैसे याद करोगे? S for Schottky, S for same number of cations and anions are missing. Schottky defect में same S for Schottky, S for same number of cations and anions are missing from the lattice sites. Okay. Okay, now let me discuss your Frenkel defect. Okay, now I'll just show the diagram. तुम लोग अभी खुद का खुद definition मुझे दोगे. ये कौन सा क्रिस्टल बना रहा हूँ मैं? जस्ट देखो डायग्राम. कौन सा क्रिस्टल बना रहा हूँ मैं? Which crystal am I doing? Ideal? Ideal? Okay. So Frenkel defect, what am I going to write down? Frenkel defect means someone give it a try. चलो give it a try. क्या हो रहा है Frenkel defect में? So one of the ions, कौन सा ion? Generally cations. One of the ions, generally cations, are missing from the lattice points. One of the ions, generally the cations are missing from the lattice points and occupies the interstitial position, and they occupy the interstitial position. Matlab they occupy the position in between the ions. Okay, they occupy the position in between the ions.
Yes, sir.
So Frenkel defect में क्या हो रहा है? One of the ions, कौन सा ion? Generally cations. One of the ions, generally cations, are missing from the lattice sites. But do they leave the crystal? Are they leaving the crystal? No. They are missing from the lattice site, but they occupy the interstitial position like this. So as a result of defect, they leave the lattice points, but they occupy the interstitial position. So this type of defect is known as a Frenkel defect.
Yes,
Okay,
sir.
and why the cations are missing? Why not the anions? So the thing is that since the cations are smaller than anions, obviously you must be knowing this, they can easily fit into the interstitial position. Since the cations are smaller, cations तो छोटा होता है, so they can easily fit out. लेकिन anions तो बड़ा होता है, so anions यहाँ पर fit नहीं होगा. So generally cation will be missing from the lattice side. So generally cations क्यों लिखा हमने? Because the cations are small in size, so that they can easily fit into the lattice points. ठीक? Is it understood?
Sir.
Fine. अब तुम लोग मुझे बोलो consequences बोलो one by one. What will happen to the density of the crystal?
No.
क्या होना चाहिए? Yes.
Same.
Yes, because the ions are just missing from the lattice points, but they are still present inside the crystal. They have not. और ये stoichiometric है, ratio तो अभी भी 1:1 ही है. रेशियो तो अभी भी 1:1 ही है. 6 cation है, 6 anion है. डिफेक्ट क्यों डिफेक्टिव बोल रहे हैं? क्योंकि लैटिस पॉइंट से मिसिंग है ना. ये लैटिस पॉइंट में होना चाहिए था लेकिन नहीं है. लेकिन ये क्रिस्टल के अंदर ही है. कहां पर है? इंटरस्टिशियल पोजीशन. सो द नंबर ऑफ आयंस आर नॉट चेंजिंग, दे आर नॉट डिक्रीजिंग. सो द डेंसिटी ऑफ क्रिस्टल क्या होगा? चलो राइट इट डाउन. डेंसिटी ऑफ क्रिस्टल
Remains the same.
remains the same. Density of crystal remains the same. Now, what will happen to electrical neutrality? Again, number of cations and anions same, so it becomes electrically neutral. Same.
Sir.
Stability again decrease होगा क्योंकि holes create हो रहा है. Stability तो decrease होना ही है. अब फिर से यहाँ पर vacant spaces create हो रहा है. Vacant space create होने से तो ions can migrate. Electrical conductivity increases, so खाली density remains the same. Other will remain. The other points are not going to change. Other consequences are not going to change. So conditions तो बोल सकते हो. Conditions क्या होना चाहिए? क्या होना चाहिए condition? Should the cation and anion be of comparable size? बिल्कुल नहीं. So condition होना चाहिए. The cation must be what? Bigger? No. Smaller than the anion. So example, silver halide, say silver chloride, say silver bromide, silver iodide, zinc oxide, etc. Say lithium iodide. So there's a vast difference in size between lithium and iodine. Okay, so why have I told you to underline? AGBR shows both Schottky as well as Frenkel defect. And number 2 is here, the crystal should possess low coordination number. So yes, this type of diagram will come. ये diagram आएगा, ये diagram से पूछेगा तुम लोगों को. The following, with respect to the above diagram, answer the following questions. It illustrates what type of defect. What will happen to the density of the crystal? ओके ये सब क्वेश्चन पूछेगा विथ रिस्पेक्ट टू दिस डायग्राम. सो डायग्राम पहचानना पड़ेगा. स्कॉटकी में कैटायन एनायन दोनों ही मिसिंग होगा, लैटिस पॉइंट से. फ्रेंकल में कैटायंस मिसिंग होगा, लेकिन मिसिंग मतलब क्रिस्टल छोड़ के नहीं जाएगा, रादर दे विल बी ऑक्युपाइंग द इंटरस्टिशियल पोजीशन. ओके, and यहाँ से expected question, why alkali metal halides do not show Frenkel defect? Because alkali metal halides में the halides ion are big in size. Okay, the alkali metals, sorry, the alkali metal halides, why do not show Frenkel defect? Because these alkali metal ions, they are big in size. Sodium ion, they are big in size, so they cannot fit into the interstitial points like this, right? So alkali metal ions, due to their large size, they cannot fit into the interstitial position. The alkali metal ions, due to the large size, cannot fit into the interstitial position, so they cannot show a Frenkel defect. So it's easy, na? It's difficult to apply.
Easy.
You're finding it easy? It's difficult.
ठीक है सर.
It's easy, na? Easy. You can rate this as very easy. And the best part is that ये पूरा आता है boards में. The best part is that this will come. So today we have finished off with the stoichiometric defect. Right? So अभी दो defect है और एक non stoichiometric है, एक impurity defect है. So I shall do that in the next class. Okay. So you copy all of these. Those who have finished copy.